Recording in progress.
Perfect. Okay. So how would you do a problem like this one? You're asked to plug in 100, 1,000, 10,000, be accurate to 4 decimal places, find the horizontal asymptote, does it have a vertical asymptote, and then rewrite this as a stretch and a shift. Okay. So we'll go through all the motions here. First off, you probably should use a graphing calculator to plug in those big numbers. Let me actually pull up mine right now. So let's see here. Here we go. Map apartments. So usually what I'll do for something like this when I have to plug numbers into a function, I'll go to y equals. So this is all being recorded, so you can watch this whenever you want to. 2x plus 3 divided by parentheses x plus 1. So I actually am storing the equation as y1. And when I quit to the home screen, if I hit second mode to quit to the home screen, if I hit alpha trace, you can call it y1. Wow, she was like really angry. What's going on? Oh no. All right, so you get 100. Sorry, you plug in 100, you get that. If I plug in 1,000, so by hitting alpha trace, you can call up y1, any equation that you store there, and then put a number inside the parentheses. It treats like f of x notation for you. And if I hit second enter, it repeats the most previous entry. So I don't have to retype all the stuff. Just make little changes. So that's all you do. You just simply punch in those numbers. So if I write the answers out, it's going to be 2.0099, 2.0009, and this will be 2.0001, I think. If I'm correct in a... Actually, no, this will be 2.010. Let me fix that really fast. There we go. So yeah, that's what's happening there. The horizontal asymptote will be y equals 2 because that's what horizontal asymptote is. Like what does y approach as x gets really large? It's getting closer to 2. Is it vertical asymptote? Yes. It's going to be x equals -1. It basically is what makes what makes the denominator equal to 0. But mind you, this is after you simplify. There's another thing that can happen called a hole. I'm not sure if we're going to talk about that, and maybe we'll talk about that today. But it's after you simplify, when the denominator is 0, that's what you do. And then for here, if I do long division and rewrite this, that goes in 2 times. 2x plus 2, 2x plus 2, subtract, you get 1. So plus 1 over x plus 1. So you can rewrite it like this. So it all makes sense that 2 is a horizontal asymptote, -1 is a vertical asymptote. So that's how you go about the whole process there. So let me do this as a screenshot. There we go. All right. Next up, number 2. Oh boy. Okay. You're asked to write this as a single fraction. So I'm going to multiply this by t and t. I'm going to multiply this by x and x. I'm going to multiply this by 2 and 2. What I'm doing is I'm trying to get rid of the fractions right away. So you get t squared plus 1 over t squared. You get x over x squared plus y squared. And you get root 3, just root 3 over 1. If you want to call it that. So you can turn up, please. Thanks. Appreciate it. So it's that simple. That's all. You just find what the denominator is for everything, the least common denominator, multiply top and bottom of the complex fraction by that. Things should cancel out nicely, and you just get that as your answers. I'll save that as a screenshot. For here, this is just old stuff that we've done in the past. You got to find the LCD in each case. So here, the LCD is going to be 20. Here, the LCD is going to be 5 parentheses 2 minus x. And here, the LCD is going to be x plus 2, x minus 2. So for this one, I'm just going to multiply top and bottom by 5, 5, 4, 4. So you get 5x plus 10 plus 4x minus 12 all over 20. So 9x minus 2 over 20. Here, you got to multiply top and bottom by 5, 5. 2 minus x, 2 minus x. So you have 20 plus 2x minus x squared all over 5 parentheses 2 minus x. I think we're good there. And lastly, here, multiply top and bottom by x minus 2. X plus 2 for that one. 6x minus 12. Negative 4x minus 8. So you get 2x minus 20. You get that. Does that make sense? How I did that one? Just all old school stuff. All right, save that as a screenshot. Here, oh, this is interesting. Okay. They call this partial fractions. If you factor this, what do you get, guys? Yeah, totally. So what's going to happen is I'm going to probably multiply this by x plus 4x plus 4. And multiply this by x plus 1, x plus 1. If I do it correctly, I get ax plus a plus bx plus 4b all over all this junk. Okay, hopefully that makes sense, right? Now here's the deal. Ax plus bx, I'll lump them together. A plus 4b, I'll lump those together. X plus 1, x plus 4. Now this is the part that's not terribly clear, but I hope you guys can see this. So what do you have on the left side? You have a 1, right? And you have the denominator like this, right? So you just have plain old 1 on the left side. Do you see any x on the left side in the numerator? No, right? The numerator on the left side does not have an x. What do you think this has to equal, this combination of ax plus bx? What do you think that has to equal? Do you guys see why that has to be 0? Why do these two combine to 0? You see any x over here? You don't. I see, these denominators are the same, so these numerators have to be the same. This 1 has to equal all this jump here. But if there's no x over here, this has to be 0. Therefore, what does this have to be? A plus 4b. Exactly, good. You got it. So what this tells me is that a plus b has to equal 0. If you factor out the x, a plus b has to equal 0, and a plus 4b has to equal 1. If you do substitution, a equals negative b. Yeah. I'm gonna put on your final, but no one else's, since you asked. So congratulations, Alex. You just custom made your final exam. The answer is no. Actually, to be honest, this is something that we do in BC calculus. Yeah. This is actually BC calculus type. It's a tough one. It's a tough one. It is. Yeah. And yeah, to be able to kind of like extend yourself at that moment, it is a little tough to do. I agree. This is actually done more BC calculus, but it's a cool problem nonetheless. Then a plus 4/3. Then so the a has to equal negative 1/3. I think it worked itself out. So those are the values of a and b. Save the screenshot. Okay, so yeah, that's kind of weird one. Not a test question, not a final exam question. I think Ms. Wong made this homework, and it's a cool problem. I like it a lot. But I think 2 could be a final exam question. Definitely 1 is a test question for sure. Because that's kind of what we've been doing. Okay, this is definitely a test. Well, actually, this is a final exam question. This is from the previous unit. But you guys should know your x-intercepts here, right? What are your x-intercepts here?
0.
Right, and we had this on the test. And there's any bounces at all? Why bounce at 3? Exactly, because you see a 2 there. Exactly right. The y-intercept, if you were to work it out, I think is 9. No, 0. The y-intercept is 0. So 1, 2, 3, 1, 2, 3. I'll just do a few more tick marks. Here we go. Yep, here we go. And the end behavior is going to be like this because both arrows, you have your degree is 4 and your leading coefficient is positive. So it's going to be up, up because your leading coefficient is positive. Leading coefficient is positive. And you bounce again, we're at 3. So it's going to look like this. It's going to come there, kind of curl up a little bit, bounce there, and do that. There's a graph. Here, for number 6, that'll be x equals negative I, or plus or minus I, we'll say. Square both sides, it'll become that. So you have x squared plus 1 equals 0. Boom, done. That's all you got to do. Here, x equals 1 plus minus root 2. X minus 1 equals plus minus root 2. If you square both sides, you get this. X squared minus 2x plus 1 equals 2. X squared minus 2x minus 1 equals 0. I wonder if Ms. Wong's voice will show up in my video here. Here I'm like just talking calmly, and she's like really loud. Okay, anyway. So we got that. Okay, so it's all good. We're cool with that. All right. And I think that covers the homework. Cool. Let me take a screenshot of that. All right, cool. All right, so hopefully you guys are comfortable with that. Let's move on to a new lesson. So still feeling rational. Okay. So what are we going to do here? Hopefully we don't have to graph all these because that would not be cool. What do they want you to do? What happens when polynomials are divided? Your teacher will assign each group a function below, substitute in large negative values of x, and observe what happens, and write the end behaviors for each. Okay, here's what I'm going to do. I'm going to use Desmos, and we're just going to look at what happens for maybe the first. Let me do this for A, C, and F. Sorry, A, C, and D. Let me do this for A, C, and D. And then we can draw a conjecture for the ones we do not do. So do A, C, and D. Okay. So, and we're going to use Desmos. Desmos will be our best friend here. Okay. So substitute large positive and negative values. Let's use Desmos and observe what happens. And then write the end behavior. So in general, we're going to write the end behavior like this. I'm going to do a text box. It'll be much easier. As x approaches positive infinity, as x approaches negative infinity. And let me copy and paste this. There you go. Okay. So make our lives a little easier. All right. So now I'm going to go to Desmos. And I do need the notes in front of me. Cool. Found right here. Everyone's got the notes, right? I got extras. I need extras. All right. Are you still feeling rational? Okay. So when you put in Desmos, you're going to be mindful that you're using parentheses. So x, you could hit Shift 6 to do the exponent. Minus 12, divide x cubed minus x squared. Probably get rid of these parentheses here. All right. So what's happening as we go forever to the left and forever to the right? What do you see is happening here? If I go forever to the left, forever to the right, where's y approaching? Let's see what is y getting close to? 0. Good. 0 in each case. Yeah. Yep. You got it. Perfect. Okay. Let's do the next one. Next one's going to have 3x squared plus 4x. And down below, negative x squared minus 12x. Okay, interesting. Did I do that right? Seems a little funny to me. Oh, no, we're good. We're good. Okay. So let's look over here. As I move more to the right, what's happened to y? What do you think y is approaching, guys? It's getting closer to what value? No, y. Here. You have negative 2.922, negative 2.9. Like, it's going slowly, right, for y? Probably, what do you guys think? Yeah, probably -3, right? Let me zoom out. Same thing here, right? It's a less than -3, but it's getting closer to -3 from the bottom. So in this case, I'm going to say -3. And there's a reason why that's happening. I'm going to get to that in just a little bit. And then lastly, for part D, let's make x3, x squared minus 12. Okay, now what's happening here? As x gets bigger, what's happening to y? What is y doing when x is bigger, guys? Does y ever have a limit, or does it keep going up? Yeah, or it keeps going down the other way. So in this case, I'm going to say pos infinity and negative infinity. Now there's a conjecture we can make, like a kind of a pattern that we're noticing. And this is very important. This is actually probably one of the most important things we do in this unit, because it kind of sets a tone for what you're going to see next year in pre-calculus. I know that what's going to happen here, it's going to be 0 and 0 again here. Here it's going to be 5 and 5. And here it's going to be negative infinity and positive, I think. If I'm not mistaken. Yeah. Okay. Let's talk about it. Now, this is the part where I kind of need to go focus. All right. So, first fraction, right? What's the highest term here? X squared, right? What's the highest term here? Okay. If I plug in, like, say, 100. That's 100 squared minus 12. That's 100 cubed. Oh boy, minus 100 squared. What happens when you multiply 100 and 100? How many zeros you get when you do 100 times 100? How many zeros? 4. Yeah, 10,000. Yeah. 10,000 minus 12. Okay, how about if you multiply 100 3 times? How many zeros you get? 5. 4. 6. 6. A million. It's a million. That's crazy. 1 million. Okay, we'll just use money as a good example. Would you rather have $10,000 in the bank or $1 million in the bank? Million. $10,000 is gone after a month. Probably mortgages. And that's it. $1 million, you could probably live comfortably for a good year and a day, right? Just kidding. Or 2. I don't know. I'm just joking. Maybe 5 years. But here's the thing. A million's a much bigger number than 10,000. That's a concept. A million's a much bigger number. So overall, this fraction getting smaller or bigger when the denominator is large. Well, let's see. Overall, it's getting smaller. Yes. Yeah. So overall,
but the denominator is getting bigger.
yes, overall, the fraction gets small. So that's why when x approaches positive infinity or negative infinity, it's 0. That's also why the horizontal asymptote is y equals 0. So there's a connection there between them. So the horizontal asymptote is not necessarily a boundary you can't touch. It's really more of an NDA. You can actually cross 0. This thing could equal 0. Actually, if I were to solve this, actually no, it can't be 0. I lied because it can't divide by 0. But sometimes this could equal 0. There are cases where, so it's not so much a boundary you can't touch. The horizontal asymptote is more about what does y do when x gets really large. That's really what's happening. So I see the same thing here because notice that you have x squared and you have x cubed, right? That's interesting. We see the same thing happening here. Now let's take a look at part C. If I plug in the hundreds, I get 3 times 10,000 plus 400 minus 12. Here I have negative 10,000 because the negative on the outside minus 1,200. So overall, I get 30. What's that? 30,388 over negative 11,200. Overall, what is that fraction unit get closer to? Like you have 30,000 or something that's close to negative 10,000. Overall, what is that like roughly? If you had to give like a whole number, not whole number, an integer. But if you're doing 30,000 over like negative 11,000, like what is that getting? Like what integer do you think is getting close to? Probably -3, right? It's getting close to -3. And if you plug in like say 1,000 for x or 1,000,000 for x, ultimately what's gonna happen, these terms don't matter. How come those terms don't matter? Because they're small compared to x squared. They're small compared to, so you really just focus on leading terms. You get -3. That's why that's 5 down here as well for e. Notice that these degrees are the same. When the degrees are the same, we're seeing that happen. Lastly, for D and F, what's happening here? If I plug in 100, I get 1,000,000 here. Here I get 10,000s minus 12. So I have a really large number up top. And, you know, not large, but not as large of a number down below. Overall, what's happening to this fraction is x is bigger. Does this fraction ever converge to a certain, or does it just keep rising? It keeps rising, or it will get more negative, right? So there's no limit here. There's no limit at all. Likewise with e, but it has to be negative. It has to be reversed because you're doing x cubed over negative x squared. So there's actually a negative there involved. So it flips things around. So here's the key takeaway. This is the big part. So if your function is this plus dot 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 plus dot dot dot, where m is the highest exponent for the numerator, n is highest exponent for denominator, there are 3 cases. There's this case, there's this case, and there's that case.
What's the M?
Oh, sorry, say that again.
The M.
The highest exponent for the denominator. I wrote right here. And m's the highest exponent for the numerator. If m is less than n, as we saw for both a and b, y equals 0 is your horizontal asymptote. I'll put HA for short. If m equals n, then y equals a over b, the ratio of the leading coefficients, is your horizontal asymptote. Here, you have no horizontal asymptote if m is greater than n. They'll always be true. So this is something that we cover often in pre-calculus. It's actually a big part of pre-calculus. By the time you get to calculus, this is second nature, because you have to kind of just know this. This actually plays a huge role in calculus, this concept here. But we see numerically that this makes sense. We play in large numbers for x. Graphically, we saw it too. And now, you know, we could approach this from an algebraic standpoint, which I don't think will necessarily. Well, we could actually do a division, which actually I think that might be what they're going to lead us to in the next page. I think. Let's find out. Okay. So using a number line and sign chart for a graph. Okay. So first off, we're just going to write inequalities. I think that's all they want us to do right now. Yeah, we're just writing inequalities here. We can keep things simple. So what inequalities do you think you'd write for part A? X is in between what 2 numbers? And what would you say about this one right here? X greater than 4, totally, 100%. Yep. Let's take a look at C, because B is a little complicated. What would you say for C? X is less than what, and X is greater than what? Or 4. Yep, perfect. You do have to use the word or as well, because it can't simultaneously be both. Never use and, guys, because can X simultaneously be less than -1 and greater than 4? No, it's one or the other. Let's look at D. X is between what 2 numbers? Here and here. And fine for this one, you actually have to write it as 2 separate ones because 0 skipped over. Let's fix that. Or 0 and 2. Okay. Go ahead. Oh, dude, I'm sorry. You have got to tell me when that happens. And because I use black as well. Of course you can't tell. Thanks for. You got it now? Good. Yeah, that's all. So we're going to use this process for the next example. Then we're going to dissect example 4. And I think I'll kind of let go. Well, we should do example 5 too. Okay, we'll see how this goes. I think we can get this done pretty quickly. I think we can get done by 1:50. Enjoy 15 minutes of sunshine. All right, so we're good. All right.
I don't get.
Okay, yeah, go ahead, yeah. Part.
Yeah, there's 3 things.
So zero skipped over, so you have to write 2 separate inequalities. So because it's skipped over, because you can't just say it's between -5 and 2. That's not good enough.
Okay.
Because otherwise you're saying 0 will be included, right? So you got to deliberately skip it over. Okay, let's keep going. Create a number line for the polynomial functions. Okay, so here's what you do for this kind of problem. You want to find the x-intercepts. Then do a sign chart. I'll explain how that works in just a sec. And actually, I kind of screwed up for number 2 because it said to sketch a possible graph and write a possible equation. I just wrote the inequalities. It's all good. It's fine. But here's what we're going to do for P1. I'm not going to do all these because this will take too long. So here's what you do. You locate the x-intercepts. Where are the x-intercepts here, guys, for P1x?
2.
Perfect. Good. Then what you do is you test values in each interval. So in blue,
You get the 3 and the -6 from.
I made them up. Let me rephrase that. Test random values in each interval. So the x-intercepts act as your partitions. See how I partitioned that number line with the x-intercepts? Does that make sense? So -2 and -5 are your partitions. And I'm testing random values in each interval. Okay. So what you do, we'll make a little table. Sure, go ahead, yeah. Okay, if I test it out, what do you get? I get -8 times 1, which is -8. If I plug in 0, I get -2 times 25. Now if I test 3, I have 1 times 8 squared times 64 is 64. So what's happening here is that everything's positive here. Everything's positive here. Everything's negative here. So this is going to be, these right here are the signs of the y coordinates. Okay. Those are the signs of the y coordinates. Any y coordinates that's less than -5 for x will be positive. Any y coordinate between -5 and 2 for x is positive. Any y coordinate when x is bigger than 2 is now negative. If I were to graph this, I'll go to Desmos to graph it. And then we'll come back to this sign chart. So this right here is called sign chart, by the way. Let's call it a sign chart. This is actually one of the most important skills in pre-calculus. Like it might seem a little confusing at first. You do this often in pre-calculus. It's actually pretty standard. X minus 2, x plus 5. Let me clear my screen for a moment. Okay, so what's happened to y before I get to -2? Sorry, was that -2? Sorry, -5. Y is negative, right? And then what happened at -5? We bounced, right? And is y still negative? And then when does y become positive? After I hit this next intersection. Now all of a sudden it's positive. Let me bring back the sign chart. Oh, wait one sec. Oh my gosh. I'm sorry, guys. I totally mixed this up. I meant to say negative. My apologies. Oh my goodness. My apologies. That was terrible. Okay. Y coordinates are negative when x is less than -5. Y coordinates are negative between -5 and 2. Y coordinates are positive when x is bigger than 2. My apologies. Okay. So when I look at the graph, let me clear this again. When I look at the graph and I look at the sign chart, the sign chart confirms the graph. Any points that are less than -5, y is negative. Any points where x is between -5 and 2, y is negative. Any points where x is bigger than 2, y is now positive. Also, this is another thing we noticed too. If I go back to the, hold on, Hunter. If I go back to this, notice that saw a square here, right? I told you guys there's a bounce. The reason why you bounce is because y never changes from negative. It stays negative the whole time. Yes, it's 0 here, but it never changes sign before after -5 because of that square. Because when you square something, it doesn't change sign, right? I mean, of course, that's negative, fine. That's like -6 or -1 or 2, that's negative. But this x plus 5 square bit never changes sign from the square part. That's why you're bouncing, that's even exponent. There's no sign change there. And so this helps to understand what the graph is doing. Hunter, go ahead. What's the question?
Do this some stuff on.
Well, ask for it, yeah. Yeah.
What's the point?
What's what?
What's
The point of it is that when you graph these, you know where the graph's going to be, whether the graph's going to be above or below the x-axis. This will help for any kind of graph you do, not just polynomial, but rational functions. Some stuff we start graphing trig stuff. There's a lot of other types of functions you'll see down the road where this will be incredibly helpful. It does help for when you get to calculus, or if you have to find like the maximum profit of some finance equation you're dealing with, and you got to find where the profit's positive, because sometimes profit can be negative. You can lose money, right? It has huge implications in business as well, because you need to see whether you're positive or negative, where we see a sign change as well. So it has, for calculus, you do this all the time. Like talking about calculus, they do this daily, sign charts. So sign charts is, but we're just scratching the surface of this right now. Let me do one more of these with you guys, just so you get the hang of it. It's not that hard once you know what's going on. I'll do P4 because it's a little crazy. So here's P4. Where are my x-intercepts here, guys? 1 and 5. Perfect. So I'm going to partition. Now, what I'm going to do when I test my values, I'm going to start with the rightmost interval. If I put 6 in, right? And you don't have to actually calculate it. You don't actually have to calculate it. Just think about it. Is 6 plus 3 squared positive? Yes. Is 6 plus 1 positive? Yes. Is 6 minus 1 positive? Yes. Is 6 minus 5 positive? Yes. What happens when you multiply a bunch of positives? What do you get? A positive. Perfect. So the graph's going to be above. So y is positive here, which means the graph is above the x-axis. When x is bigger than 5. It crosses at 5, but when x exceeds 5, the graph would be above the x-axis, because y is positive there. Now, here's what I'm going to do for the rest of this. I'm lazy, but I want to show you guys how to be efficient. I know the answer is going to look like this now. I think I was able to do that without punching numbers back in the page. I think I didn't memorize this, by the way. It's the first time I've seen this page. And I'm pretty sure if I graph the number, I'm actually 99.9% sure, right? But why am I so confident? What do you think?
because, at least when I did it, I just saw how many negative values I have in order even.
Okay.
By multiplying. So, like, when I plug in -1, I have 2 negative things in there.
Okay, I mean, yeah, so you're still punching numbers, but we want to get away from that though. Want to get an idea?
Oh, no, it's,
Well, where's the bounce happening, guys?
um,
There we go. There's not supposed to be a sign change there. Because that's an even exponent, But all the other ones are odd exponents, right? If all the ones are odd exponents, I'm using sign change at 5, 1, -1, but not there. I'll not see a sign change there. So what this means when I graph it, I'm gonna do a quick graph right now, and I'm gonna go to Desmos just to make sure I got this. I'll do a quick sketch down the bottom here. Okay, my x-intercepts are, and by the way, I could totally overlay this, right? 1, 5, -1, -3. See how the coordinate plane overlays really nicely with it? And if I just do this, the end behavior is going to be, what's the degree here, by the way, guys? What's the degree? If you have all the exponents, what do you get? 5. Arrow's going to go like this. Okay. So I'm going to bounce here, cross through here, cross through here, cross through here. And there's my graph. My graph should look like that. Now let me go to Desmos and punch it in. X plus 3 squared. X plus 1. X minus 1. X minus 5. There you go. It's not perfect because I could try smushing the graph a little bit, but you can see if I get rid of all the other junk. See how it's above the x-axis when x is bigger than 5? And see how like it goes down and up? I mean, it hits the x-axis at -3 and bounces off at -3. And then comes a bit down, then hits at -1, is above the x-axis, gets down to 1, goes below the x-axis, back to 5, and back above the x-axis. So that's what's happening. The high and low points, you can't do it until you get the calculus. Like, how do you know how high this goes? Like, how do you know it's going to hit that point? You won't learn that until you get the calculus. You have not learned that. And by the way, when you do get the calculus, in order to do that problem, you got to use a sign chart. That's how people do. People use sign charts to find highs and lows. So sign charts are a big deal. All right. We're almost done for today. Okay. So let's talk about this right here. I won't do 5. We'll skip 5 for today. We could do that on Monday, or maybe I'll just, I think you'll get the point after I do 4. I think we're good. I think it's a little overkill. Okay, x-intercepts. That's when the numerator equals 0. Because think about it, when the numerator is 0, what's 0 divided by anything? 0, right? So you set that equal to 0. Or you could write like this. Take out a 4. Vertical asymptotes when the denominator equals 0, because you can't divide by 0. So if I set that equal to 0.
What's the denominator?
The bottom of the fraction?
Well, yeah. You just said. Okay.
Yeah, of the equation we're dealing with, yes. X is 0 or 1. So you're going to write x equals 0 and x equals 1. Oh, question, Gus?
What does it say under right where your cursor is? With the H in step 1.
Oh, numerator.
Oh.
The numerator equals 0. That's all. Okay. Find the end behavior. Well, because m is less than n, remember m is equal to 2 and n's equal to 3. Those are the highest exponents. Your end behavior is going to be like this. As x approaches -infinity, y is approaching 0. As x approaches +infinity. So basically, a horizontal asymptote is y equals 0. That's a horizontal asymptote, y equals 0. Because think about it, when x gets really big, the denominator increases more quickly than the top end because the x cubed on the bottom. The bottom is a higher degree than the top does. So y equals 0. Draw a sign chart. So I'll do that right now. So the top is going to look like this. X minus root 12. X plus root 12. The bottom factor at x squared, right? So what you want to do when you do the sign chart is you're going to want to use x-intercepts and vertical asymptotes, because that's what makes the thing 0 for both top and bottom. 0, 1, root 12, negative root 12. All the signs will change here, except at 0, because 0 is squared. So there's no sign change here. Trust me, that's what happens. If you were to plug in a number larger than root 12, the whole thing's positive. Then you'll see a change in the sign at all these different boundaries or partitions, except for at 0. And these can be your partitions.
I don't know whether it's something negative.
So what I did first is I did in my head. I did quickly. So great question, Hunter. I apologize for not taking more time with it. Over here, I know everything's gonna be positive because if I plug in like say 5 for example, positive, 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 all together is positive. So I factor it. Even though this is not factored, I force the factor issue. And because these are all single factors, except for x squared, I'm gonna see sign changes like most of these partitions, except at 0. Because why do I have 0 as a partition to the x squared? Because of x squared, if I were to plug in numbers,
Isn't that undefined?
for 0 exactly, but numbers slightly bigger than 0, slightly less than 0, we're not getting, like for example, if I put like 0.1, that's negative, that's positive, that's negative. Overall, a negative, positive, positive, negative, we multiply and divide all that, that's positive, right? If I put in something less than 0, like negative 0.1, negative, positive, positive, negative, when I multiply that together, it's still positive. Because x squared didn't see a sign change. That's the reason why. And the reason why these are the partitions in the first place is because each of these numbers make each of these parts 0.
So you just look at the positive or negative.
Right, because you want to see what makes all the factors 0, because that's when you see a sign change of y. And that's where we want to see sign changes y, because that's when we know where we break the x-axis, or whether the graph is above or below the x-axis.
Yeah.
I'm not plugging in. I'm being efficient here. I know the right way to do it. Not the right way, sorry. The right way to teach it to this audience is by brute force, but I think you guys are gonna go crazy if I do that. So I'm trying to show you an efficient way right now. So I have 1, 2, 3, 4, -1, -2, -3, -4. Root 12 is in between what two integers? Or what two whole numbers? Yeah, totally, 100%. Right. So I'll put a dot here, and you have vertical asymptotes here. A vertical asymptote at 1. But we're not going to make you draw this from scratch on our test, just so you know. It's a little much right now. Most likely is to say, find me x-intercepts or what are the horizontal asymptotes. We'll ask those kind of questions, but no, it's a little too much right now, I think, for you guys. And if I generate the graph, because I know it's supposed to be positive, but negative. So the graph's going to probably look something like this. And kind of come back down like that. Over here, it's going to be kind of funny. It's going to kind of look like a parabola. And here, it's going to be positive. It's going to hit this. It's going to dip down a little bit and then kind of curl back up. It's a really weird graph. It's an incredibly weird graph. And I definitely don't want to do number 5 with you guys because, yeah, you guys will go crazy. So anyway, it's a very funky graph. Just to make sure I got this, I'm going to plug some Desmos really fast and we'll be done for today. y equals parentheses.
These are right, remember.
Sure, yeah, totally. Yeah, you can see how it's kind of hard to tell. I really don't like how this is scaled, but yeah, you see, I pretty much have the same thing. It breaks the x-axis and kind of comes back down, and then there's also a little, really hard to tell, but a little thing right there as well. So yeah, but that's pretty advanced. Like you guys will see some pre-calculus. We're not gonna make you guys do this. That's a little too much, I think. So we're gonna stop there for today. We won't do the last example. Homework's connect to this. I still don't have the finer details about tests. I'll have to stay out till Monday. If I do find out later this afternoon and do it deep here, I'll put a video on it and share it with you guys. So, yep, we're all set.